So what is the time complexity of this slow algorithm, which is computing the convex hull? If you look at the details of the pseudocode, you see that we have a for loop, and this for loop is running for all the pairs in the given set. And so this means that we have about n times n number of pairs. And then what do we have? If you look at here, we have a kind of a for loop once again. If this until this valid statement is true, so that means we have two loops inside each other, which means that it's kind of quadratic in time, and even maybe a bit more than that. So we can say that this is a very simple algorithm. Depending on the number of inputs, it actually grows in a quadratic manner. And that's why actually now we will talk about a better algorithm which computes this convex hull of the given cells in linear arithmetic time. Before that, let's talk about a degenerate case. So what do you think what happens if you have some number of points which are not actually lying to the right or to the left of these direct edges? For instance, you may be talking about such a portion, such a direct edge between, assume that this is P and this is Q, you may have such a direct edge. And if you look at the sides, the points are, some of these points are on the direct edge. You cannot say that these points are on the left or on the right. These points are exactly on the direct edge. So you need to update the algorithm. The algorithm we discussed a moment ago may fix the fifth line of this algorithm so that if you come up with such a case, you actually don't break your algorithm, you don't stop and you handle it somehow with different approaches. You may maybe neglect them, or you may assume that these are on the left-hand side. It's up to your modification, and we don't have a unique solution, but there are many solutions. But let's have a look at a bit different algorithm, a much better algorithm in terms of time complexity. And for that purpose, we are kind of using an incremental approach. And what we are going to do, we will sort the points according to their x coordinates. And then we will start working on the point having the smallest x coordinate. For instance, this is again, the same set of points. As you see this time, we have new terms, upper hull. This is the upper part of your convex hull, and then we have the lower portion, which is obviously at the bottom part. And after you sort all these points according to their x coordinates, then you will first work on the upper hull. And once you are done with the upper hull, you will work on the lower hull, and then finally you can merge these two sides together and obtain the whole convex hull of the given set P. And yeah, these are things I mentioned. And for the computation of the upper hull, now we will talk about in the next slide. We have some basic steps. We will be adding, since it's an incremental algorithm, we'll be adding all these points one by one. So if you look at the previous slide here, we will start with P1 and then start adding the next site, which has actually a bit higher x value than the previous one. So the next one will be this one. So that will be P2, and then I think this is P3, since it has the third largest x value, and this is fourth one, and that is the fifth one. So we will be adding these values, these sites actually to our algorithm, and then our algorithm will check whether these sites are belonging to the upper hull part of the convex hull. And obviously, you can see that these are not the part of upper hull, and our algorithm should find this actually fact, whether they are on the upper hull or not. So what we are going to do, we will try to form a kind of, we will try to find whether we are making a right turn or not. since if you remember the convex hull of any given set, if you are moving around the convex hull in the clockwise manner, you should always be making right turns. So this is an important issue. If you have a left turn, then that means it's not convex. So you should forget about that, let's say, portion, and find another portion which makes a right turn. And so that's why we will always be checking the last 3 points. And these, with the help of these last 3 points, we'll decide whether that portion is making a right turn or a left turn. If it's a left turn, then we need to do modifications. But if it's a right turn, then we can keep them in our upper hull and move on with the next points. Now I will try to illustrate this issue. Yes, this is the same example once again. So we start from here. This is the first point. And then at the beginning of the algorithm, we need to have at least 3 points. So that's why I need to consider this 3. And if you form a kind of an line set here, that will be the lines actually connecting these 3 points, right? And if you look at the turn we have at the center, obviously this is a left turn. So that's why I'm going to delete this one, the intermediate one. I'm not going to include it since it results in a left turn. So I will delete and add another point. What is the next point? This is the 4th one. So now I will add this one. Let me erase it. Now we have these 3 points. The first one, the 3rd one, and the 4th one. We have eliminated the 2nd one, so this is resulting in a left turn. But let's see whether we are making a left turn or a right turn. Yes, that's it. This is our line. Oh, I'm sorry. That will be the direction we are moving. Yes, and as you see, right now at the center, at the middle of this line segments, we are making a right turn. Then that means it's fine. We don't need to eliminate the intermediate point. We can go on with the next point. What is the next point? Right now, assume that this is the next point, since these have actually almost the same X value. We'll talk about it, but right now, assume that this is the next point, the 5th one. So if I have it, then we will have such a case. And as you see, at this intermediate point, we are making a left turn once again. So that means I need to eliminate this one, delete this one, and move on with the next point. So up to this point, up to, let's say, 5th point, we have these 2 edges actually, and they are on the convex hull or on the upper hull of the algorithm. So we can keep these and continue with the remaining points in our given set P. That is the basics of the algorithm. We can go with some explanations here. So in summary, if your 3 points are making a right turn, then that means you're fine. You don't need to do anything more. But if it's a left turn, then you need to delete the intermediate one. So these are the things for the right turn. But if it's a left turn, as you see here, we need to delete the middle point from the upper hull and add another point, and you can continue these steps until you go over all the points until you come to here. So this is the site having the largest X value. And we continue these steps until you have only 2 points left in your, let's say, point sets. And after you have done all these steps, then that means you have already completed the upper hull portion of the overall convex hull. And then what we are going to do, we will repeat these steps for the lower hull, but this time we will be continuing from right-hand side to the left-hand side. So the algorithm is almost the same. The only difference is that we are this time moving in the opposite direction, but the fundamentals are the same. So let's briefly have a look at the pseudocode here. And as you see, obviously the input is the set of points in the plane, P, and the output is actually a list containing the vertices of the convex hull P in the clockwise order. So this is important. We are making use of the right turn property according to this clockwise order. So as the first step, what we are doing, we are sorting all the points according to their x coordinates, and then at the end of this sorting operation, we will have a sequence resulting from P1 to Pn, and P1 has the smallest x value and Pn has the largest x value. Then this part is actually for the, this part is for upper hull, and the lower for loop is for the lower hull of the resulting convex hull. So let's focus on the first part. As you see, we are starting from the third, let's say, point in our sequence. Since at the beginning of the algorithm, we need to have at least 3 points. So that's why this for loop starts at 3, and then as you see, it goes to n. It means that it's checking all the points in this set. So what we do, you check whether you are making a right turn or left turn. If it's a right turn, you do nothing, but if it's a left turn, what you do, you delete the middle points and go on with the next point. But if it's a right point, and then you need to add this portion, add this part actually to your resulting convex hull. And then what we do after you are done with the upper hull, you continue with the lower hull. This is the initialization step for the lower hull, and the rest is the same. Again, if you are making a right turn, you're fine. But if you are doing a left turn, you need to erase, you need to remove the middle point and add another point. So once you are done with the upper and the lower hull, then you can delete the first and the last points in the lower hull in order not to have any duplication, since these points were already in the upper hull, so we don't need to have duplication. And later, once you are done with this deletion operation, you can simply join lower and upper hull together to obtain the final convex hull of the given point set P. That is the result of the algorithm. And if you look at our actually algorithm, we were assuming that we don't have any points actually having the same x coordinates. If it happens, then what we should do, we can simply order these points in a lexicographic manner, which means that if they have the same x value, then we can check their y coordinates. We can put the one actually having the highest y coordinates after this as the first one, and then comes the one actually having the smaller y value. Another case, what happens if you have these 3 points on the same line? Assume that this is your edge. You have 3 points on the same line. So you cannot say that you are making a right turn or left turn. But obviously, you don't need to include this intermediate point in your resulting upper hull or lower hull. So what we do simply, we assume that this is a left turn and eliminate the intermediate point. So once you do these modifications on your algorithm, then we can say that your algorithm can compute any actually convex hull in a correct manner in linear arithmetic time, which is much less than the slow algorithm. So this is actually the theorem about it, the time complexity. You can do this computation. The convex hull can be computed in linear arithmetic time. And I'm not going to do a derivation about it. If you're interested, please have a look at the textbook. There's a nice derivation. You can go through it, but this is, as you see, much better than the slow algorithm. So why do we need to compute these convex hulls? Where do we need to use them? There are different domains, different fields, sign fields. For instance, you can use them in computer graphics, since you may have some 3D shapes, 2D shapes, and if you do operations on the convex hull of any object, then things will be much easier. So you can also consider the convex hulls as the bounding, let's say, polygons of any given shapes. You may use them to detect whether the particles, objects on your plane or in your space are colliding or not. This is, for instance, an example here. The original shape is in the gray region. And obviously, you can see that this is not a convex shape, a concave one. But in order to make your computation simpler, you can construct an convex shape around, so that the algorithms you are going to use actually will be much easier and you will consume less time. You can also use these convex hulls in robotics, especially planning the motion of the robots, and you may use convex hulls to have some convex shapes around the obstacles. You can also use them for some geographic information systems, in even CAD design, in computer manufacturing tools. So they are highly useful. These actually convex hulls makes your life easier. Now let me briefly talk about the 3D convex hulls. Again, the idea is the same, just a 3D version of it, but algorithm is a bit different. You can see an example here, convex polytope here. Again, we have points, this time not in 2D, but we have n number of points in 3D. And again, the idea is the same. Your convex polytope actually should cover all these points around, and it shouldn't have any concave regions. All the parts, all the regions should be convex. And again, the definition is the same. Any point actually in this convex polytope, you may pick any points, and the line actually joining these 2 points should always be inside this polytope. Otherwise, we cannot say that this polytope is a convex one. Then if some portion of your line connecting these 2 points is outside of the region, then you can say that it's a concave shape. And obviously, the number of edges sometimes might be higher than the number of vertices, and this is mostly the case. And we have a theorem about it. Assume that you have the P, which is the convex polytope, having n number of vertices. If that's the case, then the number of edges you have around the polytope is at most 3n minus 6, and the number of facets, it doesn't have to be just triangles. You can have any planet polygons, and the number of faces can be in maximum 2 times n minus 4. So how we are going to do the computation of these 3D convex hulls? We are going to use a randomized incremental algorithm. If you remember, we used them in linear programming and donut triangulation. So we start with few number of points, and then add all these points one by one, and at any point of the algorithm, we always keep our, let's say, triangulation or casting problem. The solution, a valid solution, is always available at any point of the algorithm. And we'll also do the same for the computation of 3D convex hulls. And now let me discuss the details, basics of this algorithm approach. Now, assume that we have n number of points in our set P, this time in 3D space, not on the plane, but they are all in 3D space. So how we are starting, we start with 4 points in the plane. So if you have 4 points in the space, then that means these 4 points will actually form a kind of an tetrahedron. Assume that these are some points in 3D space. Let me join them together. Right now it's 2D, but we need to have connection at the backside. So now you can assume that there's a tetrahedron, and I can say that by having 4 points in space in their general positions, we can have an tetrahedron. And obviously that tetrahedron will be the convex hull. So that's why at the start of this algorithm, we have the convex hull of these 4 points, which is the tetrahedron composed of these 4 points. So, but the only case actually you cannot have this tetrahedron is that they might be on the same plane. Otherwise, you can always form a kind of 3D shape and continue with the other points. And the remaining actually will be a random permutation. So you start with the 4 points and then add new points randomly. But while adding these points one by one, we should always maintain the convex hull while we are working on the remaining, since we said that it's a random incremental algorithm, and at any point of the algorithm, you should maintain the convexity of this 3D shape. So at any point, actually what we are doing, we are transforming the previous convex hull into the new convex hull. So we can assume that we have such a transformation between the convex hull of the point set PR-1, which means that we have the points up to starting from 1 to up to n-r-1. And in this actually representation, we have the size starting from 1 to up to r. So at any point after algorithm, actually, we are doing kind of transformation between the previous convex hull, 3D convex hull, to the new 3D convex hull. And actually, there are 2 cases, not complicated. In one case, your point PR, the new point, might be inside your available convex hull, or it might be outside the available convex hull. So if it's inside, then things are simpler. You don't need to do any computation. The next actually convex hull will be exactly equal to the previous convex hull. But if your point is outside your convex hull, then that means you need to do the computation and obtain the new convex hull. So how we are actually obtaining this new convex hull? This is what we do. Now we are assuming that our PR is outside the convex hull in previous convex hull, which is CH of PR-1. This part is actually our previous convex hull. We are adding a new line, new point, and as you see, this is outside our convex hull. So this time what we do, we try to actually, you can assume that this is a kind of a light source, kind of a sun maybe, and it's shining on our planet. You can assume that this 3D convex shape as a planet, and sun is actually shining on it, and obviously we have an horizon. This red part is actually our horizon, and the gray regions actually are not exposed to sun. We don't have light on this region, so you can assume that this is the shadow of actually our 3D shape. Then what we do, actually we do computations with this horizon. Since if you have this new side here, then what we do, we actually connect the vertices of our horizon to the new side PR. So that's why we kind of actually form new triangles around this horizon. That's a very simple operation. We have here, as you see, 1, 2, 3, 4 visible triangles, but obviously we have many of them on the other side of it. So this is a simple operation we do if the new point PR is outside the convex hull, outside our planet, then we form new triangles between the horizon and the new point PR. And the thing is that sometimes you may have some facets on the gray regions which are coplanar with your Neve triangle. If that's the case, then you need to do a bit more computation. You need to erase this intermediate edge on the horizon. Since they are coplanar, you need to represent them as a single facet. So this is the only thing you need to do other than forming the triangles. The rest is highly simpler. So this is actually how we do the transformation. The left-hand side show you the initial convex hull, and then after the transformation, we have the final convex hull with the addition of PR. And as you see, we have Neve triangular faces formed around the horizon. And as I said, if any of these actually faces which are closer, which has actually connections to the horizon, if they are coplanar with your Neve triangles, for instance, assume that this is the fourth facet you have, and then assume that this is 8 triangles you formed. If 4 and 8 are coplanar, then you should remove this edge, which is the horizon actually, this horizon. It should be removed, and you need to have a new facet. Obviously, this will not be a triangle. It will be a polygon, and this is the only operation you need to do after creating these triangles. So this is what I mentioned about the coplanarity. So that's it actually, is how we obtain the 3D convex hulls of the given set of 3D points. And this is a pseudocode for the 3D computation, but I'm not going to go through it. These are the things actually we mentioned in the previous slides.